Hi everyone, I'm Jim White, and in this video we're going to discuss getting electrical power from thermocouples. Both the metallic type thermocouples and the semiconductor type as are used in what's called thermoelectric generators or Peltier devices. So let's get started. Well, here's my setup to investigate the properties of metallic thermoconductors. And what I have here is two short type J thermocouples that are soldered to the end of my soldering iron. And I've turned the temperature down to where it won't melt the solder anymore. And in this way we have sort of a controlled temperature. So the two thermocouples are connected to the same hot source, and right now the top display is one of these thermocouples. Actually, this thermocouple is connected to the number 30 thermocouple wire, which goes to the meter. And that's all legal since they're the same metal. The copper's connected to the copper, and the constantin's connected to the constantin. So these two thermocouple connections don't influence the outcome here. Now to the other thermocouple, I have connections to this voltmeter, and I see it's on the camera, it's flashing around. The update rate must be syncing with the frames per second of the camera. So at any rate, with the, by the way, we're in roughly a 24°C ambient. That's T2 there. So if I go to T1 minus T2, there's 118°C, 119. You can see it's varying a little. So let's call it 125°C. And at that temperature difference, we have 6.16 millivolts out of the thermocouple. Okay, so now the question is, how much current can this thermocouple deliver? So I'm going to connect a milliamp meter, and we're on the 400 milliamp scale. Okay, I'm going to connect the milliamp meter, and you see we're reading 0 at the moment. And now we're reading roughly 2.6 milliamps. So I'm writing that down. Okay, now I'm going to change to the 10 amp input. And now we're showing 10.4 milliamps. And we're down to 1.09 millivolts. I forgot to get the voltage output when we were on the 400 mil scale, so we'll go back to that. Okay, we're a little higher than we were, but all this is ballpark stuff right now. Okay, on the 400 milliamp scale, we have roughly, we'll call it 4.8 millivolts. Okay, so the mysterious thing is why on the 400 milliamp scale are we reading 2.6 milliamps, but when we go to the 10 amp scale, we're reading 10.7 milliamps. And the reason is the input impedance of the ammeter on the two different scales. And I'm going to go calculate those input impedances because it turns out they're important in determining the true capabilities of a thermocouple as a power generator. So I'll show you the calculations next. Okay, here's our data tabulated. We were using a type J thermocouple, and we had a differential roughly of 125 degrees C. And under open circuit conditions, which would be no current flowing, the voltmeter was showing roughly 6.16 millivolts. So when we were hooked up to the 400 milliamp scale of the ammeter, the ammeter showed 2.6 milliamps, and that dropped the voltage to 4.8 millivolts. So from the voltage and current, we can calculate the input resistance of the milliammeter, the 400 mA scale. It's roughly 1.85 ohms. Then we switch to the 10 amp scale, and we measure a voltage out of the thermocouple of 1.09 millivolts, and our current was reading 10.4 milliamps. So we can also calculate the input resistance of the meter, including its leads, as roughly 1/10 of an ohm. So we can form a equivalent circuit for this thermocouple, and of course this would change based on the temperature differentials and so forth. But at any rate, we had a 6.16 millivolts at open when there was nothing connected to the terminals other than the voltmeter. And at that point there would be zero current. Now when we hooked up our meter on the 10 amp scale, we read 10.4 milliamps, and our open circuit voltage dropped down to 1.09 millivolts. So we can calculate the resistance of the thermocouple when we had 10.4 milliamps flowing. Whatever the resistance is, there was 5.07 millivolts across it, which is the 6.16 open circuit voltage minus the 1.09 terminal voltage at the time the 10.4 milliamps was flowing. So that turns out that the resistance of the thermocouple is roughly 1/2 an ohm. Well, here's some data that I overlooked, which would be important for comparing thermocouples. All the measurements that we made here are based on a thermocouple that was 6 inches long, which is roughly 15 centimeters. And the wire diameter was 22 thousandths of an inch, which is 24 gauge wire. And you can get thermocouple wire in various gauges, and depending on how long you make it, the conditions will, and the measurements will change, of course. So let's go back to our test bench and see what else we can learn about the thermocouples. Okay, here we are back at the test bench, and what else can we learn from our setup here? Well, what if we were to connect those two thermocouples that are connected to the soldering iron in parallel? Let's do that and then repeat the measurements that we made. Come up backwards, but it doesn't matter. The meter will just read negative. Okay, this time we have about 19 milliamps negative because I hooked the meter up backwards. Okay, when I connected the amp meter, the voltage went down to 1.92 millivolts. So let's go repeat our calculations. It's kind of obvious that we've almost doubled the current, and even though we're at the same output voltage. So obviously the resistance went down and we're getting more current out. So let's go calculate it. Okay, with two 24 gauge thermocouples in parallel, we see essentially the same open circuit voltage for roughly the same temperature differential. But when we connected our current meter, the terminal voltage dropped down to 1.92 volts, whereas with a single thermocouple it dropped down to 1.09 volts. So at any rate, if we go through the calculations, the internal resistance of the thermocouples comes out to be 0.23 ohms, which is about half what it was for the single thermocouple. So, but basically we can see putting two thermocouples in parallel is the same as using a fatter thermocouple wire. Now, you can get up to 16 gauge thermocouple wire, which is 0.065 inches in diameter, which is 1.65 millimeter, compared to 0.56 millimeter for the 24 gauge. Well, if you calculate the areas, the 16 gauge is 8.7 times the area of the 24 gauge. So the half an ohm that we calculated for the single thermocouple, not the two in parallel, was divided by the 8.7 is 0.056 ohms. So now the current for the 6.2 millivolts output with the 0.056 ohm resistor is 111 milliamps. So that's over 1/10 of an amp. That's looking pretty good. But let's run our temperature up to 700 degrees Fahrenheit or Celsius difference. So the current would be 5.6 times bigger. That's the 700 divided by the 125. So we'd be up to 0.62 amps. Okay. Now, there's a theorem called the maximum power transfer theorem, which says when you have a fixed voltage and an internal resistance, the maximum power you can deliver to a load is when that load ohms is equal to the internal resistance ohms. And you can calculate that for yourself. Just calculate the power with resistances out here a little bigger and a little smaller than that value, and you'll see. So the current with a load equal to the internal resistance comes out to be 310 milliamps. So the voltage across this resistor is 1/2 of the generated voltage, and the current is 310 milliamps. So the power delivered to the load is 1/2 the voltage times the 310 milliamps, which is 5.39 milliwatts. So if we put up 1,000 of these thermocouples in series at the maximum power, we'd have 17.4 volts at the 310 milliamps, which is a whopping 5.39 watts. Now that's with 1,000 thermocouples with 16 gauge wire connected in series. So you can see this is pretty difficult to do, to get any reasonable amount of power out of this particular metallic thermocouple. Okay, back in the lab, and here we have a high power thermocouple. It's made with a number 8 copper wire, which is 0.128 inches in diameter, and a piece of steel, which is 0.030 inches thick and 1/2 inch wide. Now it's been silver soldered at the end so that it can withstand high temperatures. Now let's see what kind of voltage we can get out of this. So we have the meter here. Okay. This meter has a minimum and maximum feature, and I'm going to use that because we're going to reach a maximum and then go down as I heat this thermocouple, and I'll explain why. Okay, here we have a little mini torch. Okay, the meter beeps every time it records a new value. So you see the voltage climbing there. Oh, it stopped climbing. I'm still holding the torch on the end. Okay, it's now going down, even though the torch is still on there. And the reason is the copper wire is conducting heat, and it's actually quite toasty down here by this alligator clip. I can barely touch it. So that's one of the problems with metallic thermal conductors or thermocouples, is the conduction of heat along the length of the thermocouple. And after this cools off, we'll do that again, and we'll record the current and see how much current it can produce. Okay, I have the ammeter hooked up now, and we're on the 10 amp scale, and I have it set up again to record minimum and maximum. So I'm going to begin heating the thermocouple. Okay, there we've reached maximum and we're falling off. And it's the same reason. The heat conducted to the other end of the thermocouple has made it quit working. So we had a maximum current 12 milliamps. Okay, here we are back in the lab, and here's our high power thermocouple again. And if you watched my video on measuring the Earth's magnetic field, you have seen this before. And it's a circuit to feed a Hall effect device. And what I've done is taken a toroid like this and milled a slot through it and inserted a Hall effect device. And then I glued all that to a little piece of circuit board so that it could be handled. So what we have here is basically a DC current transformer. If I put that on here, I can measure the current in the wire without inserting any resistance into the circuit. So I'm going to short the other ends of that together, but that'll take 2 hands, so we'll turn off the camera. Use that clip to hold the ends of the thermocouple together. And I've already calibrated the current transformer. Well, I don't want to call it that, but our measuring device here. And it's 64.2 millivolts out of it is equal to 1 amp. So here's our millivolt meter, and I'm going to put the torch on the thermocouple again and see how much current we can get. Okay, we peaked out at 7.5 millivolts, and if we had a way of cooling this end, we could maintain the current. Like if we had this end in water or something, then we could get rid of the heat that's coming down the copper wire. So let's do some more calculations, see what we have. Okay, here's the results from our experiments with our large thermocouple, heavy duty. We had an open circuit voltage of 1.348 millivolts and a short circuit current of 0.117 amps. As you can see, thermocouples don't put out a lot of voltage, but they do put out reasonable amounts of current. So at any rate, if we divide the voltage by the amps, we find our thermocouple has an internal resistance of 11.5 milliohms. So again, using our maximum power transfer theorem, if we match the load to the internal resistance, we get a load current of 0.0586 amps. Now if we put 1,000 of these in series, we'd have an output voltage of 1.348 volts, and at our maximum current we would be able to deliver 0.079 watts. So just using regular thermocouple wire, a 16 gauge, we got many times that output power. So just using readily available materials is very hard to get any reasonable amount of current or power out of thermocouples. Okay, that was kind of a rough thing to get through, but if you stuck with me, I think you see why using metallic thermocouples to produce reasonable amounts of electric power is very difficult. You need very low resistance, and low electrical resistance generally means good thermal conductivity. So it's hard to keep the cold end cold. And so it's kind of difficult to do anything meaningful with these. So along came this module, which is done with semiconductor thermocouples, which have the advantage of at least 10 times the Seebeck coefficient and much greater thermal resistance. So these are called thermoelectric generators, if that's what they're used for. Sometimes they're called the Seebeck generator. When they're used for cooling, they're called Peltier modules, and sometimes they're just referred to as thermoelectric modules. So in the next video, we'll dive into these things and see what you can do with them.